Alright, I'll start this one with number 3. I think it'll make number 1 a little bit easier. So we have an x component of a vector and a y component of a vector. The y is in the negative direction. So here's my negative y direction and here's my positive x direction. We just go ahead and draw. I'll start with Vy. That's going to be 6.4 units, kind of arbitrary units, in that direction, in the negative y direction. The x component is going to be 9.8 units in the positive x direction, so I'll kind of draw that guy like that. And I'm looking for, what is this vector v? So I'm looking for both the magnitude, the length of it, as well as the direction of it. So what I can do is I can say, well, let me take Vy, and I'll just kind of move it over here, just like that, and I'll add these guys in the tail to tip method. So here I have, you can see here, a triangle with the x being that side, the y being right here, and the hypotenuse being v. I know from Pythagorean's theorem that the length of v, that's what those little absolute value signs mean, is going to be vx squared plus vy squared. So the length of v is going to be the square root of vx plus vy. Both of those guys are squared. So the length of v is going to be the square root of 9.8 and then 6.4. That's going to be squared right there. So the length of v must be 11.7, and it's going to be arbitrary units. Now I'm looking for the angle here. I know the adjacent side and the opposite side, so I'm looking at a tangent. The angle is going to be the inverse tangent of Vy divided by Vx. So that's going to be the inverse tangent of 6.4. Divide that guy by 9.8, and I'm going to get 33.1 degrees. And just to kind of specify, that's going to be below the x-axis. Okay, nice little vector problem where first we're going to have a car that's driven in the westerly direction, and then it's going to turn and it's going to drive in the southwest. So I'll set up my axis kind of like this, where I have west over here and south over there. So first thing the car is going to do is going to travel. It's going to have some displacement in the westerly direction right there. It's going to be 225 kilometers. Then it's going to turn and it's going to travel in the southwesterly direction. That's going to be at a 45 degree from displacement from the westerly direction right there. So that guy's in blue. And I'm looking for the length of this resultant displacement right here. I'm looking for how long that guy is, and I'm also looking for the angle that it makes. So to solve this, what we're going to do is we're going to look at this southwesterly, this blue vector here, and we're going to break it first into its, so we're going to break it up into its westerly component. So that's going to be d southwest in the west and d southwest in the southerly direction. We're going to add these two guys together, and that's going to be the resultant displacement in the y direction, and this is going to be the resultant displacement in the southerly direction. And from that we can figure out the length and the angle. So let's take a look at this triangle right here. It's a 45 degree triangle, so I can write d southwest in the westerly direction. That is the adjacent side of the triangle, so it's going to be the hypotenuse multiplied by cosine of 45. Hypotenuse is 98 kilometers, d southwest, multiplied by cosine of 45. That's going to be 69.3 kilometers. Similarly, d southwest in the southerly direction, that's going to be the hypotenuse, 98, multiplied by sine of 45, or 69.3 kilometers as well. So my displacement my resultant displacement in the westerly direction, that's going to be the sum of those two. It's going to be d southwest in the west plus d west. So that's going to be 69.3 plus 225 kilometers. That's going to be equal to 294.3 kilometers. D resultant in the southerly direction, that's just d southwest in the southerly direction, or 69.3 kilometers. And I know that the length of my resultant displacement, the little arrows right there, can be related to its two westernly and southerly components. The resultant is going to be following Pythagorean's theorem, really. D resultant in the southerly right there. Essentially, we have a triangle right here, and we'll use Pythagorean's theorem to write the length of the resultant vector. Go ahead, and I want to take the square root of both sides, and I can write my resultant displacement. It's going to be the square root of d resultant in the westerly direction, so 294.3. It's going to be squared. And then d resultant in the southerly direction, 69.3. That's also going to be squared. So we're going to be left with 302 kilometers. Now that's only part of the puzzle. We also want the angle. We know that right there, that's the result in the westerly direction. We know this guy right here, the result in the southerly direction. So I know the opposite and adjacent sides. So I know that the angle must be equal to the inverse tangent of the westernly side, the southerly side, d resultant in the southerly, d resultant in the westerly. So inverse tangent of 69.3 divided by 294.3, and we're going to come out with 13 degrees, and this is going to be south of west. So now I'll be working a vector problem kind of in reverse. Now I know that an airplane has got some velocity, and it's got a length and a direction. And what I'm looking for is I'm looking for the northerly component of it. So the northerly component of it. And I'm looking for the westernly component of it. So V in the west. I can also kind of maybe move V in the west up here. And I have a nice little triangle with an angle of 45 degrees. So I can first maybe solve for V west. That's going to be the opposite side, and I know that so it's going to be V multiplied by the sine of the angle there, so it's going to be 835 kilometers per hour multiplied by the sine of 41.5. So the velocity in the westerly direction is going to be 553 kilometers per hour. So there's that part of it. Similarly, the velocity in the northerly direction, that's going to be V multiplied by, now it's going to be the adjacent side, so it's going to be the cosine of that angle. So 835 kilometers per hour multiplied by the cosine of 41.5, and we're going to come up with 625 kilometers per hour. Now it's asking how far north and how far west. Well, we know that the velocity is going to be equal to the change in position divided by the change in time. So if I'm looking for the change in position to the north, that's going to be the velocity in the northerly direction multiplied by the change in time, or I'll just write time in the time of flight. Now I know that the plane traveled for 1.75 hours, So in the northerly direction, it's going to be 625 kilometers per hour. In the northerly direction, I'm going to multiply that by 1.75, and the unit's going to be hours. So you can kind of see, leaving the units on here, hours are going to cancel out and I'm left with kilometers. So my displacement in the northerly direction is going to be about 1090 kilometers. Same thing for the westerly direction. My displacement in the westerly direction, that's going to be equal to the velocity in the westerly direction multiplied by the time. I know that the velocity in the westerly direction is going to be 553, so 553, and it's going to be kilometers divided by hours. I'm going to multiply that by 1.75 hours. I'm going to cancel out my hours right there, and we're left with a change in position to be 968 kilometers in the westerly direction. So let's look at kinematics in 2 dimensions. I'm going to have a tiger. The tiger is going to be leaping off of a 7.5 meter high rock. So 7.5 meters, that's going to be my y distance. I've just got to draw my tiger. It's going to leap horizontally, so it's going to have a horizontal, or x, velocity that's 3 meters per second. It's leaping horizontally. It has no vertical component. It has no y component to the velocity, so v naught y is going to be equal to 0. And I know that this cat's going to essentially go some distance, and that's kind of what I'm looking for. I'm looking for how far away does it land. I also know that it's going to be accelerating. It's going to be accelerating downwards. So that's going to be my acceleration. Acceleration is going to be the acceleration due to gravity, so 9.8 meters per second squared. You can kind of see all my motion is going, or all of my vertical motion is going to be in the downwards direction. I might as well say, you know what, rather than keep track of a whole bunch of negative signs, I'm defining that to be positive. So down is going to be positive, my acceleration is going to be positive, and my displacement is going to be positive, rather than keeping track of all these negative signs. So, you know, what you do is you say, well, let me look at all my equations for kinematics right down here. I have my x and I have my y. You can kind of see in the y direction, there's really nothing that has any x in there. The one thing, however, that both the x and the y share is going to be time. Time is going to be the same in the x as in the y direction. So what I need to do is I need to figure out how long it takes the tiger to hit the ground using my y direction. I know everything I need to solve for time in that direction, and then I can apply that in the x direction. I know in the x direction it's not accelerating, so it's just going to be distance is equal to rate times time. So looking at my equations of motion in the y direction, this equation right here is going to be the best one to use. I want to solve it for time, and I know some positions, but I also know that, you know, that's going to be equal to 0, and I know that that's going to be equal to 0. So really I'm kind of left with is the position is equal to 1/2 the acceleration in the y direction multiplied by time squared. So time is going to be equal to, I'm going to multiply both sides by 2, and then I have my y right there. I'm going to divide both sides by the acceleration and take the square root of both sides. So that's going to be 2 times 7.5. Divide that by the acceleration, 9.8. And I can go ahead and I can solve for my time and say that my time must be equal to 1.237 seconds. Now, I know in the x direction there's no acceleration, and so I can say that the velocity in the x direction is simply going to be equal to the change in position divided by the time. So my change in position is going to be equal to the velocity in the x direction multiplied by time, which is going to be 3 meters per second multiplied by 1.237 seconds. You can see the seconds is going to cancel each other out, and we're left with 3.7 meters. So let's take a look at another projectile problem. I'm going to have a football, and we're going to kick that football. It's going to have some initial velocity, and essentially it's going to go up and come back down. And what I'm looking for is, how much time does it take before it hits the ground? Well, I'm going to say, well, this is going to be my ground, and my initial position, my y0, I'm going to say that that's 0. It goes up to some height, it's going to have some height of y. It's going to come back down, it's going to have some final height. That final height is going to be the ground. It's also going to be 0. We also know that it's going to be accelerating. It's going to be accelerating at the rate of gravity, 9.8 meters per second squared. And I'll say, okay, this time I'm going to call down is going to be negative. So my acceleration is going to be downwards. It's also going to be negative. My v0 is going to have a component in the y direction. That's going to be in the positive direction. It's upwards. So what I need to do is I need to break up my velocity into its x and y components. So my initial velocity in the x direction, my initial velocity in the y direction. Now in the x direction, motion is just going to be constant. It's going to have that initial velocity throughout the entire time of flight. In the y direction, it's accelerating downwards. That velocity is going to get smaller and smaller and smaller. It's going to touch 0 right here, and then it's going to get larger and larger and larger until it hits the ground. So I'm going to write v0y. That is going to simply be equal to the velocity. It's going to be multiplied by the sine of the angle that it's kicked at. That's also going to be 18 multiplied by the sine of 31. So v0y is going to be 9.27 meters per second. So I go down here and I say, well, let's take a look at my equations for the y direction here. I'm looking for time, so this is the equation that I want to most likely use. I know that y is going to be equal to 0. I know that y0 is going to be equal to 0. So what I'm left with is 0 is equal to v0y multiplied by time plus 1/2 acceleration times time squared. What I can first do is I can say, well, I'm going to divide everything by time. So divide everything by time. 0 divided by time is still going to be 0. I'm going to cancel out a time there, and I cancel out one of my times there. Then I'm going to say, okay, I'm going to subtract v0y from both sides, and I get negative v0y is equal to 1/2 acceleration times time. I'm going to multiply both sides by 2 and divide both sides by acceleration. So put my 2 divided by acceleration right there. Everything's going to cancel out there, and cancel out there, and I'm left with my time of flight to be negative 2 v0y divided by the acceleration. So negative 2 times 9.27 meters per second, acceleration 9.8 meters per second squared. It's downwards, it's negative. We can see that the negatives are going to cancel out, and I'm going to be left with 1.89 seconds. Last problem is going to look very similar to the previous problem. Here I have an athlete, that's my box right there. It's going to be launched upwards at some initial velocity. They're going to go up and come back down, and they're going to land, and we know that this distance right here is going to be 7.8 meters away. That's going to be my horizontal distance. Now I can again break my v0 up into v0 in the y direction and v0 in the x direction, and I could even say, I know that v naught y is going to be equal to v naught multiplied by the sine of the angle. It tells me it was kicked at 27 degrees. And I can also say something similar. V naught x is going to be equal to v naught multiplied by the cosine of the angle that it was kicked at, so 27. And I know in the y direction it's going to go up. It's going to have a 0 y velocity, and then it's going to come back down. It's going to have a negative velocity as it comes back downwards. In this particular case, I'll say downward is going to be negative. So my acceleration will be negative 9.8 here. In the x direction, we don't have any acceleration, so we can just say distance is equal to rate times time. But the one thing that these two guys are going to share is going to be time. So what I need to do is I need to solve for time. I'll do that first using the y parameters. I'm going to say it's going to start off on the ground. The ground is 0, so y naught is going to be 0, and similarly y is going to be equal to 0. I'm going to use the same equation as last time. I'm going to say y is equal to 0, y naught is equal to 0, and so I'm going to end up with 0 is equal to v naught y multiplied by time plus 1/2 acceleration times time squared. Go ahead and I divide both sides by a time. That's going to cancel out. Subtract v naught, multiply by 2, and divide both sides by a. And I'm going to end up with an expression for time that says time is equal to negative 2 multiplied by v naught y divided by a. In the x direction, I know that I can simply say that the position is going to be equal to rate times time, v naught x here, multiplied by time. This time is, again, shared between these two guys. I can take that time and plug it in right over there. So v naught x multiplied by negative 2, v naught y divided that by a. Now I can say, well, I'm going to have negative 2 v naught x v naught y divided by a is equal to my distance. I know what my distance is. I'm looking for v naught, so I need to take my expressions for v naught x and for v naught y, these guys right up here, and plug them right on in. And I'm going to say that my position is going to be negative 2. And here I'm going to have v naught cosine 27, and then I'm going to have v naught sine 27, divided everything by a. Now what I want to do is I'm going to have negative 2 v naught squared sine 27 cosine 27, divide everything by a. So I'm going to solve this guy for v naught. I'm going to multiply both sides by a. I'm going to divide both sides by 2, divide both sides by sine 27, divide both sides by cosine 27, and I'm going to be left with v naught squared. So I'm going to say v naught squared is equal to x multiplied by a divided by sine 27 and cosine 27. Divide both sides by negative 2. Take the square root now of both sides, and I'm left with v naught is equal to the square root of x multiplied by a, negative 2 sine 27 cosine 27. Bring that square root all the way out there. I go ahead and I plug all those guys in where I say x is equal to 7.5. Acceleration is now going to be negative 9.8 meters per second squared, and sine and cosine 20 and sine of 27 cosine 27. At the end of the day, I'm going to get my velocity to be 9.72 meters per second.